After many years of failure, Uber has finally figured out how to minimize customer wait times.
Let's go! I've got places to be, come on!
Unfortunately, there have been some unintended consequences.
It was already weird when he started yelling at me, but then he started going 50 in a school zone. I don't know how many kids he nearly missed.
He didn't even stop the car for me to get out. He just slowed down and expected me to jump. So you may have figured out that the project is about Uber. We wanted to model the system in the San Francisco area. The goal is to find the wait times for the riders, and the wait time is defined as the difference between the time from when the Uber is ordered to when it actually gets to the customer. Most of Uber's major markets have competing services like Lyft in the US, Ola in India, and Yaxi and Easy Taxi in Mexico. So it is in Uber's best interest to try to reduce their wait times. We have 3 simulation models for this project. One is the base model, the next is a model with self-driving cars, and the third is a model with checkpoints. We are going to compare the wait times for all of these and see which one yields highest customer satisfaction. We've also made certain assumptions while simulating the outputs. One is we assume that the distribution of the rider requests remains steady throughout the day. The number of drivers remains the same throughout the day as well. We've assumed an average velocity that the drivers ride at, and we've also assumed a uniform distribution for demand throughout the city. We also have a few possible sources of error. One of them is the human source, which could be just by lost communication between the rider and the driver. The third is technological problems with inaccuracy in GPS. And the final one is unexpected traffic patterns.
We decided to use Python to implement our project with permission from the TAs. We did this in order to avoid the limitations of Sigma. Python was also easier to read and make quick changes. We have 3 different models. Each model has the following files: an event file that holds an event class, a system file that has the system class including the priority queue acting as the event list, a sim file that takes the next event of the priority queue, executes its state changes, and schedules the next events, and an event functions file that is the main code of each event and node. The only difference between the models is the event functions file.
So this is the base model for our simulation. It follows the standard no initialization as the starting point. And what this initialization event does is we have this map, which is part of our simulation. It represents, in our case, the city of San Francisco, where we would be taking Uber requests for customers to travel from a point A to a point B. So an initialization event, it sets up the location of the drivers. For example, if we have 3 drivers, their starting locations would be distributed uniformly within this space. So for example, we have a driver here, here, and maybe here. Afterwards, it would schedule the arrival of the first customer, which is RR, which stands for rider request, which is also happens to be self-scheduling. At this point, the rider's location would be randomly generated uniformly within the space. So for example, let's say a rider appears over here. Additionally, the rider's end location will also be generated. So for example, this rider may want to travel to this spot on the map. It also happens to be self-scheduling, so the inter-arrival times of riders is distributed in our case normally. So after the rider appears and it goes to AD, or checks if there's an available driver, then it sends a request to the nearest driver. So in this case, it seems to be probably this driver. So we move on now to driver request, DR. So this driver would set its state to be busy and start driving over to this rider, pick it up, drive to the end location, EOD, which becomes free again. And once the driver is free again, it's available to start serving another rider. In order to improve the response time of drivers in our system, we decided to extend our base model in 2 different ways. One is what you see here, which is we call the driverless model, and the other is the checkpointing model. For the driverless model, we decided to change our drivers into self-driving cars. So unlike normal drivers, these self-driving cars don't need to take brakes and whatnot. So basically what happens in our system is the speed associated with these self-driving cars is faster compared to normal cars. So as you can see, our model compared to the base model still has the same events. But in this case, the state changes associated with driver response and time it takes to drive, so end of drive event, is decreased because of the increased speed.
This is our checkpoints model. It is one of our 3 models. It is very similar to our base model, but it has a slight difference. Whenever drivers are idle, meaning they're not taking a rider anywhere, instead of standing still, they are actively moving towards the center of the board, the checkpoint. So that's why it's called checkpoints. So how this works is very similar to the base model. We initialize the riders on the board. They're all initially free. Then we have a rider request node that keeps calling itself. So each rider, it's how often a rider appears on the board. So that's a rider appearing like right there, just randomly, uniformly throughout the board. Then we call an update drivers event whenever a rider request is made, because the driver is actively moving towards the center of the board. All the free drivers are actively moving towards the center of the board. So when the rider request is made, we need to determine where all the drivers are. So they're right here when the rider request is made. Then the update drivers calls an available drivers node, and that node checks all the drivers' locations that were just updated and checks which drivers are free and which of those free drivers, which one is the closest to the rider. So it will determine that, oh, this driver is the closest to this rider, so it will schedule a driver response node in time TD1, and that time TD1 is the amount of time it takes for this driver to get to this rider. Now this driver is still free, so it's moving still towards the checkpoint while this is happening. The driver response node schedules a end of drive node in TD2, and that's the amount of time it takes the driver and the rider to get to the rider end. After the ride is ended, the driver becomes available, so update driver location is called.
In order to define our distributions for travel times, we referenced Uber Movement, which is a really handy online tool that stores different service times in major cities around the world over time. So specifically for our models, we pulled from San Francisco in October of 2017. In order to construct our 95% confidence intervals on our average wait times, we used the method of replication, where for each number of drivers per model, we ran the simulation 500 times, and we held the number of events constant at 10,000. So actually for each model, we were serving a different number of customers. What we expected to see was that our driverless model would have the shortest average wait times, and that our base model would have the longest average wait times. What we actually found is that for our base model, with an input of 2,000 drivers, the average wait time was only 3 seconds, which was our shortest average wait time. However, when we took a look at our driverless model for the same number of drivers, it still only had a wait time of about a minute, and it served twice as many customers. Now, on paper, the numbers, 3 seconds compared to a minute, is significant, but in reality, to a customer who is waiting for a ride, a minute still isn't actually that long, and it served twice as many customers, which means more money for the company.